This lab is on the critical micelle concentration of cetyltrimethylammonium bromide, otherwise known as CTAB. Hi everybody. So this time I'm going to talk about the lab that we call the critical micelle concentration of cetyltrimethylammonium bromide, or CTAB. Okay, so CTAB is what we call a surfactant. It has a very long hydrocarbon chain, and on the end of that chain is a nitrogen, which is bonded to 3 methyl groups. So it has 4 bonds and it has a +1 charge. And the bromide is a counter ion. So I made up a solution of this CTAB in water. It's over here, the stock solution that I'm going to be using to make all these other solutions from. And so, well, first I would like to say, what is a critical micelle concentration? Maybe you've heard of this before, maybe not. So, first of all, when you have a detergent molecule, it's this positive charge and this negatively charged ion. So when you put them in a solution, you basically get these ions floating around, and then as you increase the concentration of those ions, at some point they aggregate. They aggregate into a very nice spherical giant particle that consists of, who knows, 50, 100 of these monomers. And we could figure out, actually, if you took Chem 408, we actually figure out the aggregation number. That's how many of these large monomers aggregate together to form what we call a micelle. So this lab, we're going to determine what is the concentration of CTAB that's needed in solution for micelle formation to start. And it turns out that after micelle formation starts, after that concentration, the critical micelle concentration, the more surfactant you put into the solution, it basically all goes into the forming of micelles. But anyway, in this lab, what we're going to do is figure out what is the concentration at which these monomers start to form micelles. So we're going to make 9 different solutions. Like I said, this is my stock solution. And we're going to start with much, dilute ones, and then we're going to get to stronger concentrations of the CTAB. And we're going to figure out, we're going to measure 2 different properties. Okay, so first of all, we're going to measure the conductivity of all those different solutions that we make. And the reason for that is, as you add monomers into the solution, you're adding something that's like sodium chloride. It's ionic, okay? So you're going to increase the conductivity as you increase that number of ions. Now, once you get to the critical micelle concentration and you get this aggregation, you don't have the same steep increase in conductivity as you increase the concentration of the CTAB. And that's because you have this aggregation that goes on. And you have a lot of those bromides are attached to the micelle, kind of associated with it, and fewer of them are actually dissociated. So, so anyway, you end up with a change in the rate of increase of conductivity with CTAB concentration. And where that break in the concentration is, where that change is what we define to be the critical micelle concentration. So one way we're going to determine that is by conductivity measurements. So I'm going to be very careful. I'm going to rinse all my flasks here with deionized water. I made the solution in deionized water. I don't want any extraneous ions coming in from somewhere. All right, what's the second method? I said there were 2. You'll notice that I have another bottle here, okay? And so what I'm going to be doing is adding 4 milliliters of this solution. This is phenanthridine, and it's a pretty dilute solution. It's about 7 times 10 to the -5th molar. But the thing about that phenanthridine is it fluoresces, okay? So if I were to take a solution of the phenanthridine, I could put it in the fluorescence instrument, the fluorimeter, and I could measure its fluorescence intensity. That's very nice. Okay, so what happens when I add it to these different solutions that have different concentrations of CTAB? Well, the phenanthridine fluorescence is influenced by whether there's micelles around, okay? If micelles start to form, then these phenanthridine molecules will actually enter into the center of the micelles. So they'll go inside the micelles because, maybe I didn't tell you this, but maybe you could get it from reading the lab handout, that the way these micelles form is that their hydrocarbon tails all entangle inside the middle of the micelle, and the heads, which are polar, are on the outside. So phenanthridine actually goes inside the micelle and sort of locates itself, it's believed, near where where the heads are, and bromide ions are associated with those micelles, and bromide ions influence the fluorescence of phenanthridine. So when the phenanthridine goes into the micelle, it actually gets closer to bromide ions. And what those bromide ions do is they decrease the fluorescence intensity of the phenanthridine. We call them quenchers. A quencher is something that takes that excitation energy that the phenanthridine has in this case, and somehow transfers it over to itself. So there would be some kind of energy transfer where the phenanthridine would no longer have that excited energy. It would have transferred it to the bromide, and so it doesn't fluoresce. We call that quenching, when the fluorescence stops because there's something influencing it. So what happens is, as the number of micelles builds up, you have more and more phenanthridines that are going inside these micelles, and the ones that go inside don't fluoresce. Their fluorescence is quenched. And so what we see is that as you get to the critical micelle, here's the fluorescence intensity. When you get to the CMC, it starts to drop. And as the number of micelles increases after the critical micelle concentration, more and more phenanthridines go inside of those micelles, and that fluorescence gets quenched quite a bit, so it goes down a lot. So we're looking again for the break in the curve to see where does that fluorescence quenching actually go down. So those are the two methods that we're going to use. What I'm going to do first, I'm going to rinse all these flasks with the DI water. I'm going to put the appropriate amount of stock solution, which I'm going to do by burette, and I'm going to make all 9 solutions. And of course I have to put 4 milliliters of the phenanthridine in each one as well. All right, so I rinsed all my flasks with DI water, as well as the this burette here. But I want to show you that when I fill this burette with the CTAB solution, I'm going to be very careful to pour it down the side of the burette, because that will stop the foaming. Because don't forget, this is a surfactant. This is basically a soap molecule, or similar detergent molecule, and I don't want a whole lot of bubbles in here, because then I won't be able to read my burette very well. So notice I really didn't get any bubbling when I poured it nicely down the side of the burette. Okay, so I'm going to put the burette over here. All right, and I'm just going to take and get rid of the bubbles in the tip. Okay, and let me get that reading of the first. So it looks to me 1.28 milliliters will be my initial reading. Write that down on the data sheet here. Okay, and my first solution, let's see, where are my directions? Oh, the first solution has 0 milliliters of the stock CTAB. And I said 4 milliliters of phenanthridine, but I lied. It's really 5 milliliters of the phenanthridine. So how about if I go directly to solution number 2, which is supposed to be 5 milliliters of the CTAB. And you know what? I think I'm actually going to let some more. I always tell students not to do this, but I don't really want to be looking at this 0.28. I just want it to be on a milliliter number. So. So that is now 2.0. Just make sure, because I don't have a very good straight-on view of that. Yes, 2.00 milliliters. So if I'm going to add 5 to solution 2, here's solution 2, I'm going to go from 2.00 to 7.00. That's what I'm aiming for. There's 7.00, so I got that. So that's what I'm going to do. I added my 5 mils to solution 2. I'm going to have to add 10 to solution 3 and 15 to 4, etc. Okay, so that's what I'm aiming to do while I turn the video off. But at the same time, I'm going to get a 5 milliliter pipette, and I'll start worrying about the phenanthridine. So just to let you know, I'm still plodding along at this. I'm going to be making solution 7, and I'm going to be putting 30 mils. So from 0 here to 30 down here. So here's my solution 7. And I've had to refill this burette quite a few times, and I'll have to refill it more. But I thought I would just show you one of these longer ones. I mean, it's really not very exciting, which is why I haven't been showing more of it to you. Oh, this is really a lot easier than pipetting all this stuff. Getting down to 30. All right, there I am, 30. Okay, and I think I'll spare you the last 2. So this one I had to go down to 35, but I want to show you that it's really very hard to avoid bubbling altogether. So there are some bubbles there, okay? And so instead of really having a meniscus, you have a bunch of bubbles. And notice that I stopped when the bubbles were at the 35. So it isn't a true meniscus, but I'm doing the best I can. Maybe I should add a little smidge more. I'll take a look at that after I stop holding the camera. All right, so now I've got all my flasks with the right amount of the CTAB solution in it, and I'm going to pipette 5 milliliters of phenanthridine into each one. So I'm going to go find a 5 milliliter pipette. This anymore. This is where, if this was a cooking show, all the people would be coming out, taking care of all my old glassware, but unfortunately this is not a cooking show. Okay, rinse with this. Let's rinse the pipette. All right, so I'm just going to pipette 5 mils. Okay, solution 1. And I'm going to do the same thing for all of the solutions. I'm going to pipette 5 milliliters into each one of them, and then I'm going to bring them to the mark with deionized water and invert and mix 10 times. So that's my next steps. One is done. So I just want to show you how when you fill this, you actually, it helps if you go down the sides of the flask. So I fill it like this, and it stops it from foaming up too much. And if I had too much foam, I wouldn't be able to see, you know, it would be harder to see where I should stop, you know. I know I can't see a meniscus, but it'll be easier if I don't have a giant amount of foam at the end. So that's why when I fill all of these, I go sort of very gently down the neck of the flask. And I'm going to get close on all of them before I get a dropper that comes out a little slower than these water bottles. Okay, so now you could see that I have made my solutions, all 9 of them, and they, had varying degrees of foaminess in them at the end. And like I said, I tried my best to get that meniscus. Well, there wasn't really, it's not really a meniscus, but to get the dividing line between where the bubbles start and the solution ends to be just about on that line. Okay. I recorded some data, so here I have basically what I did, prepared the solutions, and then what my initial and final volumes were, when I transferred the correct amount of the CTAB solution. And I also mentioned on the top that 5 milliliters of the phenanthridine was put in each one. And now I'm going to prepare to do some conductivity measurements. So I want to show you that this is this conductivity meter that I'm going to be using. And the first thing you need to do is you need to rinse it several times with deionized water. Okay. So here's the conductivity meter. You could see what it reads right now. It's been sitting here for a while. So here I have what we call the conductivity cell. It looks like this. It looks a little like it's broken on the bottom, but it's really, the place that's important is between the 2 black rings over there. Okay, that's the part of the cell that's actually the working part. So, boy, is this hard to do with one hand, but, so I'm going to basically rinse this. So I'm going to, pour out my water. See if I can get this camera a little lower down. It might work better. Okay, this test tube here is where I'll be putting the solutions. So I will rinse this several times with water, and in so doing I'll also rinse this conductivity cell out by dipping it in and then pouring out the water. I'll do that a few times. I already did it a few times behind the scenes, Let's see, I got a number there that's about 1.5 or so. Okay, so what are the units now with this instrument? It says micromo. Okay, a mo is an inverse ohm, so it's a unit of conductivity. And when we have very small numbers, we use this scale here. This scale is for when the conductivity is between 0 and 20 micromo. Okay, if we go greater than 20, we would go to the next reading here, which would give us, well, I'll show you when we get to that. Okay, so right now I think, let's see if I've rinsed enough. Ouch. Let me rinse it one more time. I ran out of water in there. So let's see if it goes down anymore with another rinsing. .34, it's gone down a teeny bit. And I wish I could have one of you remind me to record the temperature, because conductivity really does depend on temperature. Okay. We're sort of approaching a minimum value. When I started this whole rinsing process, and this cell hadn't been used for a while, I was up at 10. And with the first rinse, I was down to 3. And then you saw where I was at 1.5. So I think I'm good here. It seems to be stabilizing right there. Okay. So I guess I'll start with solution 1. I'm going to rinse once with the solution. Really difficult to do this, but okay. A little bit more. Of course, this has to go. All right. So can you see that? Okay, it says 5.67. So I'm going to take the reading almost immediately after I put it in, because there is some drift here, as you can see. So I'm just going to put it in, take the reading. It was 5.67. On my data sheet, I write down 5.67 micromo. Looks like this. Okay, and solution 1's conductivity. All right, now, so what you might notice that I've done here is I started with the most dilute CTAB solution. Solution 1 didn't have any CTAB in it. I don't have to rinse too thoroughly in this because I'm actually adding a solution with more ions as I go along. So once again, I'm going to rinse it once, making a few bubbles there. Oh, I probably should have rinsed the conductivity cell as well. Well, I'll do it again. There we go. I want to leave enough left so I can do my fluorescence measurements. All right, now let's see. You see now that 1 on there, that indicates that I need to go up to the next range. So this is 24.8. It's still micromo. Okay, I'm going to rinse that, get rid of that. Now time for the next one. Solution 3. Rinse it. Okay. And that says 44.1 for solution 3. All right, so solution 4 is next. Pour a little in, rinse it, pour it out. Okay, and I see it says 57.0. Solution 5. Looks like it says 81.4. All right, ready for solution 6. It's a bit of a mess. $93.8 for solution 6. 7. Give it a rinse. Looks like 102.1. 102.1. Getting there, solution 8. Okay, it looks like 106.9. Finally, solution 9. One 12.2. Okay, we're done with the conductivity. Okay, so we're ready for the fluorescence part. I have a single fluorescence cell and all my 9 solutions, what remains of them. And I have a set of pipettes here and a whole lot of Kim wipes. And I'm going to turn the fluorimeter on. There's actually an on-off switch here. And I turned the computer on, but I'm probably going to have to wait a little bit because it hasn't been on for a while, and there was a power outage in between. Okay, so basically what I'm going to do is rinse that cell with solution 1, put solution 1 in it, measure the fluorescence intensity, and that will be the maximum fluorescence intensity. So I'm going to try to adjust the parameters so that that first solution gives me a fluorescence intensity that's near 1,000 but doesn't go over it. So maybe I'm aiming for like 900 or something. And then for the successive solutions, they will only be lower than that. There might be some fluctuation though, so I don't want to set it to 1,000 because maybe the next one will be 1,010 and I don't want it to be cut off. So that's my overall goal, and I'm going to show you some of it, but it's a little hard to do it with one hand, so we'll see how this goes. Alright, so here's my cell that I'm going to be filling with solution 1. I have a nice clean pipette. To fill the pipette with solution 1. Give it a little rinse. Right in the waste. Maybe do it again. And then fill it up. Okay, so I've got my first solution, and what I'm going to do is I'm just going to put it in this fluorescence instrument, this fluorimeter. So I have to open the top, and there is room for 1 cell in there. I really should give this a nice wipe with some Kim wipes, which I have over here. So I'll just put the camera down and do that. Alright, so now it's all nice and Kim wiped. And now I'm just going to put it in the sample compartment over here. Alright, my instrument is turned on. And now I have to just deal with the computer. Alright, again, I have this million icons, but I pick the Carry Eclipse icon right here. After I click on Carry Eclipse, I'm going to go to the Simple Reads program. And then I'm going to set it up. Hit set up over here. And I get this nice menu box, and I have to put in what excitation wavelength I want and what emission wavelength I want. So then the instrument will shine that wavelength of light on my sample. And I'm going to set the excitation to 245 nanometers. Okay, and then the emission wavelength that I want is 368. And now I'm going to choose the slits that I want. That's basically how much light is going to get through. Alright, it doesn't tell me what the slit should be, so I'm going to put 5. Okay, and then I'm going to actually measure the fluorescence intensity as soon as I get the green light. I'll click on this for reading, and I go down here. Whoa, that's ridiculous. What's going on here? Set up. 245. Oh, because it didn't take 368. It took 600. Okay. So now when I click on read, I'm going to get a much different number. Go down, take a look at it. Ah, you see, it's off scale because it says 1,000. So what that means is that I have to go back to the setup menu. And I have to change something, either the slits or the voltage on the photomultiplier. So let's go to options, and I could put this on manual, make the voltage, oops, I didn't show you that. Go to manual here and make this like 550. I'll try that. So I've basically turned down the power of the detector read. And what is it giving me? Ah, look at that. It's 440 now. It's way smaller. That's too small. So I want it, remember, I want it to be close to 1,000, but not over. Okay, so I'm going to go back to options. And I'm going to choose, instead of 550, I'm going to make it 575. And I'm going to hit read again. And check down here what my intensity is. And I see that it's gone up. It's now 662. But I still would like it a little higher than that. So this is gotta play this game a little bit sometimes. Go back to the setup menu. And I'm gonna change this under options again. Change this to 585 and see how I do. I hit read, and now I've got 770. I still would like it a little higher. Setup. Change this number again. Let's see, under options. $590. I don't know if you could see that, but so now I'm going to do another reading. And let's see. All right, looks like we got 833. You know, I'm almost back to 600 where I started. I think 833 is fine. So now what I'm going to do is go back to setup. So what I'd like to do is increase the length of time that it will average. So here it says average time 0.1 seconds. You know, let's make it a big old 2 seconds. That means it's going to take 2 whole seconds to do the reading. And when it does, it tells me that it's 829.5. That's good enough to write down in my data. All right, so I just put solution 2 in the sample compartment, and now I'm going to get the reading, a simple read here. I'm going to hit this key and it counts all of 2 seconds. And now for this one, my number is 810.1, which I'm going to write on my data sheet here. Okay, and I'm going to go on to the next sample. All right, so now I have solution 3 in the fluorimeter, and it gives me a reading of 804.0. Write that down. Okay. Okay, I've got solution 4 right now. And solution 4's reading is 809.1. And now I'm going to go for solution 5. All right, I've got solution 5 in there now. Take the reading. $792.7. And on to solution 6. All right, I've got solution 6 now. You'll notice there's some bubbles on top. I don't see too much bubbling within this sample, but there have been samples that have had some bubbles, and that could account for some of the fluctuation in the readings. Okay, so that's solution 6 in there. I'm going to hit the read button. Go down and look at my value. 690.5. Now, what's supposed to be happening to these readings? Well, they are supposed to be going down at a certain point once the micelles start to form. All right, we're ready for solution 7. $529.6. All right, soon we'll have solution 8. Okay, solution 8. You could see these numbers have gone down. So we've got 430.3 here for solution 8. And last but not least, we have solution 9. And what do you know, it is the least. 364.9. And so here's the data for the fluorescence of solutions 1 through 9 that you can use to write up this lab. One other thing I wanted to mention was when I did the conductivity measurements, the temperature was pretty hot in this room. It's actually gone down a little bit, but it was 28.2 at the time, 28.2 degrees Celsius. Now it's changed. It's a little bit cooler in here now, thank goodness. let's see. Well, it hasn't gone down that much. It's about 27.2. Before it was 28.2. All right, so that means that the temperature when the critical micelle concentration was measured was 28.2, but with the fluorescence measurements it was about 27.2. All right, now I have solution 4, which is giving me a reading of, what the heck happened there? Interesting.